Oops. Now I'm recording. Okay, so the thing with that is, I would say, like, if this was a problem where we were just doing the square root, I would expect you to show this work. Since it's like the square root is only a part of the process, right?
Right.
I would probably maybe be okay with you skipping it on this.
Okay.
Like,
Yeah, because
doing
that would save
root
time
6.
on the test.
Yeah, and you still have to know how to do it, sort of, right?
Yes.
Matt, one thing I'm noticing that's not on the review that is on the test for sure is using the square root method.
Okay.
I mean, not that they could use this method too, but I just a reminder of the square root method might be nice.
Okay, so that was 1A. We put it in the quadratic formula. And so I know I just turned on the camera, so I'm going to like go ahead and show this a little bit how we did this. So we threw it in the quadratic formula. We simplified a few things. Just in case you need it, you can always push pause on the video. But I'll go ahead and just glance the work up at it there, and we divided that, separated it, and we ended up getting something in the complex numbers as a solution, right? Okay. Let's do something. What other one do we need to do? Part B? I think we did C and D already, right? We did A, C, and D now. What about part B? If we do part B, what is that? Minus 15, and it's going to add to positive 6. Oh, no, we can't do this with that. Never mind. We already said we're going to do this with quadratic formula, huh? Okay, so never mind. We're going to do the quadratic formula. So do we remember quadratic formula? So I want you to write it out before I write it out. I'm going to write out my A, B, and C here. I'm going to take a sip of coffee and let you write it out. Yeah, it'll work. Okay. X equals a negative B. Write out first, foist. If you're doing this quadratic formula. Yeah. Okay. X equals a negative B. So how does this one differ from the first one? I think it's just by a negative sign, huh? We're switching the C to a -5 now.
Yeah, it's very similar.
Very similar. So we're starting off with a negative B as in B squared, 6 squared minus 4 times A times C. 2 times 2.
Oops.
2 times A is 2 times 3. Their numbers, -6 plus or minus. This thing is 36. Now instead of minus, I think it gives us 36 plus 16. Over 3 is still going to be 6. Now we need to simplify root 96. I think the 96 is what?
4 radical 6.
Yes, we can divide 96 and what, 6. And so we do root 16, root 6. That's going to be 4 radical 6 all over 6. So we got a similar sort of problem here. We're doing -6 over 6 plus or minus 4 root 6 over 6.
Okay, so the plus or minus can be put in between these two fractions?
Yes, because these are separate terms. Anytime you see plus or minus or an addition or a subtraction sign between terms, it's separating terms. So this is like one thing, and I look at this thing separately.
Okay, yeah, because I didn't know what to do with that, once I started separating.
When it's being multiplied, we don't separate them, right? But when if there's like addition or subtraction, these are separate things.
Two.
So this is like one thing, and this is like whole another thing over here. First thing is giving minus 6 over 6. This should give me that minus 1, just like I got before in the previous problem. This thing, how do I simplify this thing?
Reduce the 4 and 6.
By what factor?
2
By a factor of 2. 2 divided by 4 is 2.
and 3.
So this should look like 2 root 6s. Y'all good with that? Need some more?
Yeah, and then we write it out twice to show the two solutions,
And if you put that,
Right.
that's fine with me. You can write it out twice if you really want, but
oh, okay.
that's fine.
And then we have to put the discriminant 96,
No, I wouldn't.
because
really,
that was before we simplified it, broke it down.
that was the question, and that they asked was what discriminant was, but
So if, like, let's say the discriminant is radical 96.
Uh-huh.
Is that the discriminant, or do we have to show the simplified one where it's 4 radical 6?
so the discriminant itself is just the number 96. It's not the radical.
Right, so
Just the number.
therefore it's just 96.
Yeah.
Okay. And then 2 real solutions because it's positive.
This is the 2 real solutions we're getting, yes. And they are real solutions. They are not rational, right? Because we got like root 6s in here. They won't be rational, but they will be real. So to give you a really weird number because of these radicals, but it'll still be real. Okay. New problem.
Oh boy.
How would you solve this one?
Square root.
Square root property. All right. So if I want to do the square root property, what are the steps to the square root property? What should I do on this thing?
What do you square root both x 15 and 32?
Take the square root of both what?
I feel like we're supposed to do, because since it's squared.
Mhm.
Um,
You should take the square root. There's one thing you should really do first before you start taking square roots.
yeah, like are we supposed to write it out twice since it's squared, or do we just move ahead?
You just leave it like that with the square root
Okay.
property.
Just got so used to saying a square and having to write it out twice.
Yeah,
So-
that's a good practice, but not the direction on this one.
We would square root x minus 15. But I'm sorry, no, wait, sorry. You subtract 32.
Yeah, that's the guy.
My bad.
You got to subtract this guy. So it's a little bit different when you square root property. Usually when we factor, we like one side to be equal to 0. Square root property, we like to get the square root by itself. If we do that, this is going to be minus 32 on this side. Now it should be ready for the thing you're talking about, right?
Right, square root both sides.
Square root both sides. And if I take a square root, don't let me down. What do I have to do?
Plus or minus.
Plus or minus that guy. All right, x minus 15 is this side now. We get rid of our square. We have a plus or minus negative 32. Okay. So I now have a plus or minus here. Can we write plus or minus? How bad it's getting. So I got a plus or minus. What is the first thing I should take out of here?
An I.
I should take that I out.
I got root 2. I'm sorry, wait. Go ahead.
No, what'd you say?
I got 2 square root of 2.
2 square root?
Yeah, bring it down from the discriminant.
It should be a little more you can take out. 32 is what? 2n
I got 16.
16.
Yeah, and I did 4 by 4 for 16.
Okay, so we're doing root 4 and root 16, right?
Oh crap! Right? Yeah. So
Yeah.
square root of 16.
Yeah, square root of 16 is 4. Yeah.
Yep.
It should be 4i root 2, I think, is what I'm getting.
Yep. There's that. Then we add 15 plus.
So how do we add 15 is another question, right?
So it would be on the outside, right? So
Yeah,
before square root
you
of
can
2.
either do like 15 plus or minus 4i root 2. This is
Uh-huh.
the way I would write it. The other way you could do it is you could do plus or minus 4i root 2 and then do like plus 15 over here to the right. I would put it out in front just because it looks
Easier.
it looks more like the a plus bi form,
Oh yeah, that's true.
which is the standard complex number form.
Understood. All right.
We still got to know the square root property. We got to know quadratic equation, quadratic formula. I still got to know how to factor things. That's not. I don't think that's going to leave you for the rest of the class. We're going to be factoring.
This is C, right?
This was a problem I completely introduced.
Sorry. Yeah, I got distracted. I thought we were
Completely
on
new
C.
problem. Yeah.
Yeah.
It's not in anywhere in the review.
But this particular question will be on the exam tomorrow, correct?
There might be something like it. Yeah.
Okay.
Something pretty similar. I don't remember what numbers I picked on the exam. I hope I didn't pick the same ones by coincidence. But there might be a chance. Who knows?
Right. So this
I
is
see some numbers
showing.
up there.
So this is showing like similar to the quadratic, but without specifically being the quadratic, how we're using similar steps to get to the X solutions.
Yeah, when we
Or this
derived the
form of C.
quadratic formula, we actually derived it by doing this thing and just generalizing it. It was like the same sort of process.
Okay.
We just did it with an annoying amount of letters in there, basically.
Okay.
But we were completing the squares with just a bunch of letters, and that's how we get the quadratic formula. What else do we need to do?
I think we left off on 2.
Okay, so leave us this function of a formula. Evaluate 1995 and interpret the results. What would the world population be in 2010? According to this model, when did the world population reach 7.5 billion?
We're going to draw a chart for this.
Yeah, the first two. Are they doing X as a year? Yeah, between 1950 and 2020. Yeah, this isn't a very pretty sort of thing to do. I would definitely probably just plug this into a calculator if I was doing this problem myself. But it is manageable. So the first two, how do those differ, or do you see any difference between the three problems, I guess is what I should ask, right?
Oh,
Do
yeah.
any of them look similar?
Well, both A and B are asking for the population. Well, technically, B is asking for population, but A is, well, it's asking for the results. That would also be population, but C is looking for the population at 7.5 billion. So there's a
The win. So they're asking for the year, right?
right.
So this is giving you the year and asking for the population. Or another way of saying this is they're giving you the year, they're giving you the X value, right? So this one, I hope is not the thing that's A and B, I hope are not the things that are like tripping you up too bad. Like what I'm doing is I'm taking this thing, and if you want to do it by hand, I guess you could, but it's not going to be very pretty. But it's kind of what I have in my head. I'm going to do 1995 and square it. So for these two problems, I'm probably definitely going to pull up some sort of technology and plug in my formula. Because I don't want to do this. That's kind of nasty, right? So if I do 0.00, I do x squared minus 1.13x. Ooh, forgot my plus what? 1720.1. So I believe that's my function. If you want to go to table, you could do that. If you want to pull up your variables, there's a few different ways to do it on your calculator. What I'm doing is I'm plugging 1995 into my function. So I think this should be what they're getting. Should match up. It's a bunch of like number crunching, and I don't feel like that should probably waste a whole lot of time on that number crunching, right? And so that's what they're getting in the back. I think they say 5.6 billion for this one. The other thing is if I take this and I plug what 2001 into my x. So instead of 1995, I do 2001. If you wanted to go to your table, you could do that too. That would probably work. I'm getting what, around 6.2. They said a different year, right? 2010, sorry. So it helps if you put in the right year that they tell you. That's where they're getting the 7.1 billion. The other thing should look like if I take my equation and now I'm setting this equal to it. So this is the other sort of way around, right? Is what we were saying. This is like if we take an x value, plug it in, and find a y. This is like they're giving us a y, and now we have to do some back solving for an x. So now we have our function, and we know this function should be equal to this number that they're giving us, the 7.5. Yeesh. Are they doing that to us? Okay. Do they expect them to solve this with technology, Miss Watson? Do you know?
I think definitely.
Yeah.
That's so ugly.
Do we go over an equation solver or how to do that?
I don't think we have, but
There's a way. Yeah, there's a way to do it with equation solver. Was it 1712.6? Is not a nice thing to solve. I guess we could do it with the graph too, probably, but you'd have to get the right window on your graph. That would be difficult.
Yeah. So I don't know what you're talking about, equation solver. I have the quadratic formula programmed into my calculator. Is that what you're talking about?
Oh yeah, we could do this with quadratic as well. No, I was talking about there is a. Let me see if I can find it. It's under math. Okay, so if you type this equation, so this does change a little bit because we moved this 7.5 over. So I did change my equation a little bit to set this side equal to 0. It's going to change this number a little bit, right? So I do have to change a little bit in here. If I do that, there's like this thing called math solver. It's like the last option in math.
I never knew that was there.
There is an equation solver. So my equation, I have to put in, my equation is the one that is in my y1 function. My x, so I want to pick a value for my x. I don't know. Let's just guess around the year 2000. I don't know. And then I have to go, was it alpha solve? It's alpha in the enter button. I think that does it. It gives me 2013 is how they're getting that. So that is not
That's awesome. I never knew you could do that.
Yeah, it is. And there's also a negative root here. So if you want to guess the negative root, probably you're guessing around a negative 1,000, and you go to the alpha solve, and it'll give you the other root, right? The 1770, 1780 is probably what we're going to do there. Pretty close. But we're closer to the 2,000, so we do alpha solve. You can do an equation solver is what it's called. It's under math. And they're all different depending what model you have, so it's kind of hard to tell you which one to do. It's like it's a little tweak on it on each version, you know. But you can definitely solve equations. This is not something I would try to throw at you at a test, something like this. I'd throw into a quadratic. I don't think there'd be anything quite that ugly. But if we wanted to, we could absolutely throw this into a quadratic. Here's my A, my B. My brain just really didn't want to go there because that's pretty ugly. It's like that. Okay, so it's doable. You should understand the concept a lot more than you should try to understand trying to solve an ugly quadratic, right? If I give you something for an x value, plug in the x value. If I give you something for a y value, we're going to have to do some back solving on this guy, is the name of this story. So knowing where to plug things in is really important. Knowing whether they're giving you an x or whether they're giving you a y. Is the discriminant positive, negative, 0? So how many real solutions does this thing have? That's the easy way to start this. How many real solutions would this first one have?
0.
0, because it doesn't cross the x-axis. We don't get any real zeros. If it doesn't have any real zeros, that means they probably all have to be imaginary. If they're all imaginary numbers, what does that mean about the thing underneath my square root? It had to be how do we get imaginary numbers? What do we put under a square root? Is that a weird question? Negative, there we go. Your mic not working? All right. Sorry about that. All right, so we get 2 intercepts. That means we get 2 real zeros. What was our discriminant?
Negative.
It would be negative if we got imaginary solutions. So now we're getting 2 real solutions. We're getting 2 distinct things. This is the one where it will be positive. And if we're getting the same thing over and over again, that's because we're adding and subtracting what?
0.
0. If you add 0, it's the same as if you subtract 0.
The discriminant is not the same as the sign on the quadratic, correct? So you could have like an upside down quadratic, which would be negative, but the discriminant is still positive.
Yeah, so the discriminant tells us how many times or how many real zeros we're going to get or how many times it's going to cross the x-axis.
Okay,
So if we get 2 distinct solutions, that means our discriminant was positive. So the discriminant is the b squared minus 4ac. Right? Way to say that stuff that was underneath the square root. So if the stuff underneath your square root is negative, what does that mean? It means you're getting nothing but imaginary solutions. That means it's not ever going to get any real solutions. If it's positive, you're going to get 2 real solutions. You're going to add and subtract some number underneath the square root. It might be an irrational number, but it's still going to be real. You're going to get 2 solutions out of that. But if we add and subtract 0, we're going to end up getting the same number twice. We're going to get a single solution. It's that repeated solution. So the discriminant tells you how many times you're hitting your axis, basically. Or how many real solutions you're getting. How many real zeros. Determine whether the function is odd, even, or neither. Okay, so on A, what should I probably write here? If I want to write an x to a power, I could always write x to the
0.
0 power. So, but the constant, I can think of those as like x to the 0 power. My sort of suggestion here is if it's constant, you want to write something like x to the 0. If I just see an x, what number can I put on there? I can always put an exponent of 1. So x to the first power is x. So if you do this, I think this might make your life a lot easier, probably. You might have to do something like x to the 0, like that thing. This is a square root. So we didn't go over those like too much. We did mention them briefly. But if I'm looking at the first one, is that odd, even, or neither?
Neither.
Neither, because I got a 5. This one's neither. The part B, is that odd, even, or neither?
I would
Even.
say even. Oops.
It is definitely even because we got 0 and 2. 0 and 2 are both even. Part C, is that odd, even, or neither?
Odd.
This is odd because we got 3 and 1. And what about this thing? The square root of x squared plus 2x to the 0.
Something tricky about that one.
It's a little tricky.
Even?
It is even.
Okay.
Okay, so regardless of the radical, we're still going to look at it like that.
Yeah,
correct?
and part of this is because the radical is also even. And
Oh, okay.
if I'm being honest, I should probably make y'all really like plug in the definition. If we get m of a minus x, right? This goes back to the definition and proving it, sort of thing. We're going to be able to plug it into minus x and get the same thing back. We end up getting square root, this becomes the positive x squared. We end up getting back our original function if we plug in a negative.
What if it was cubed? Would that be neither?
Was cubed. Whew. I think with cubes, yeah, I think it would be neither at that point. I would have to graph it, to be honest. I think you might still get. No, I don't know if this is square. I think you might still get that symmetry. I could be wrong. To be honest, I would have to graph that. This is kind of an odd combination. I think it would still be symmetric because you still have it minus x and the minus would still get squared. I think it would still be symmetric.
But in other words, the value on the radical could still affect it, in other words.
Yeah, I think this has the potential to affect it, and we have to see and plug things in and see if it follows the definition.
Yeah, because that one, I'm not sure.
If it was cube, I think it would still follow the definition. I'm not seeing that it would break it.
I have to watch for that.
I'm not too sure anything would break it in this scenario. As long as you have this thing inside your radical. Yeah, well, we're not trying to make them too complicated on this one. So, determine whether it is odd, even, or neither. You got multiple guess right there. Which one is odd? Let's just go with that. Which one looks odd?
B looks odd.
B looks odd. Does A look odd?
A does not look odd.
Okay. Does it look even?
Nope.
No. So it looks like it's almost odd, right? That's why I was trying to see if I could mislead you a little bit, but you caught me. That is neither. It looks like it's almost odd, but the problem with it is that it's like it's not going through the origin. It's not going to have that symmetry about the origin. This one is odd. This one's obviously odd. If we take this, flip it 180, or we flip and flip, we're going to get the same thing. This one, then, by power of deduction, you could probably guess if you didn't even know it. Even, Steven?
Because it's even over the y-axis, right?
Yes. So if we flip it across the y, that's going to be even. So this, you got to know these symmetries, right? You got to know what they look like symbolically. Now we're doing graphically. Now we're going to do what they call numerically in Roxwald. They like to have like 4 different ways they show you things or something. It's like verbally, symbolically, graphically, and numerically. Okay, so now they're doing it numerically. If we have a table, even, odd, or neither, we're looking along here. So what do we look at if they are even or odd? Hope you're looking along there, right? So we're looking along there. What do you notice about those things? Those are they the same or opposites?
Opposite.
They are opposites. 3 and -3, 1 and -1 are opposites. And what's the other thing I have to check? They're opposites, and it goes through the origin. If they're opposites and it goes to the origin, then they are
Odd.
odd. And we're looking along here. You might say, hey, I'm looking along here and I see that these are opposites. I might be thinking this is odd. But what about this thing?
Doesn't go to the origin.
Doesn't go to the origin. So what am I going to say about this one? It is not odd. Is it even? Not even. What do evens look like?
Well, I look at the x values changing, but then like the y values seem to stay the same as they cross the y axis.
Yep, those are the same. And so if they're the same, they are even, Steven, right? Like Shia LaBeouf. All right, so complete the table. If f is even, what am I putting right here?
Oh, even? Oh, okay. So I'd put a 3 and then a 5.
Yeah, it should be the same across here is what we're saying. Should be the same if it's even. If it was odd, I would throw in a negative in there, a -3, a -5. That would make it odd. Oh shoot, no, it doesn't go through the origin. So it would have to go through the origin too. Complete the graph of f below where f is an odd function.
These wouldn't have to be like perfect, but just kind of approximating.
Yeah. So if 1 and a -1/2 are a point on my original function, what's going to be on it if I reflect this thing twice? Is another way to do it.
You go from right to left, you go up a little bit, and then you turn. And then go down. Curve down.
All right, so if it's going to be 2 reflections, right? I'm going to reflect this and I'm going to reflect this.
Mhm.
Another point on here should be -1/2. And have something like what, 2, 0? So if I do 2 reflections on 2, 0, I'm going to what? Negate the 2, I'm going to negate the 0. So any point you pick on here, you do like a double negation, basically, I think is what's happening. So if I do 4, it goes through 4-3 because that's close enough. If I'm doing through 4-3, I'm gonna go through it minus 4. You're sort of like leveling off there. Okay. Where we at? Find all the local and absolute max and mins on this graph. All right, so we're doing all the extrema. So we want to do, let's do local first, local max. So how many local maxes do I have on here?
4.
I'm just talking about the maxes.
Oh, sorry, 2.
2 of them, yeah. One of them should be like right here. So what are the values for those things? What value am I looking for when I talk about my max?
Y values.
Talking about the Y values, and I'm talking about the Y values here of 1 and 3 are where those peaks hit. So I'm looking along here at 1, looking along here at 3. Those are my local maxes. My local mins would look like what and what?
There's no local max because of the arrow. I mean, I'm
There-
sorry, absolute max. Sorry.
Well, okay, we're doing local min first. and I'll
Oops,
get to
I'm sorry.
but yeah, I think you might be onto something there. So if I want my local mins look like the valleys. Local maxes look like peaks. Local mins look like valleys. So what are my local min values?
-1 and 0.
Yeah. 2 local min values. If I want absolute. What about my absolute max? That's the thing, like you were saying. If it's got an arrow going up, we're looking at absolute max, we're looking at 9, right? If it's got absolute min, what is my absolute min here?
-4.
That's where we look at everything. We can include the point when we talk about absolute things, right? When we talk about local, we don't look at points. Yeah. Problems? Okay. Questions about maxes and mins, local maxes, local mins. So really, like, think about valleys and peaks, and only valleys and peaks when you do the local min max, right? When you do absolute, look at everything. If it's got an arrow going up, guess what? It ain't got a max. If it's got an arrow going down, guess what? It ain't got a min. If it's got a point and it stops right there, that's probably going to be it, right? Okay, so identify the minimum degree of and the sign of the leading coefficient. Okay. So what do we notice about this thing? Let's do the sign of the leading coefficient. So if we're looking at the sign of the leading coefficient on this thing, and we're just going off like that. What are you thinking about? What is the sign of the leading coefficient? So you should be either thinking, does this look like a line or a parabola for the in behavior? So is this a negative or positive leading coefficient?
A?
Yeah, on A.
I'd say negative.
It's negative because it looks like a line going down. And if we want to identify the minimum degree, how would we get that?
So there's a minimum and a maximum degree, correct? Or is there just a minimum degree on
There's just a minimum degree based off of the picture based off of your turning points is what you should be counting, right? If we look at turning points, you might notice there's like 4 of them there. And so what would my minimum degree be?
Uh, 5, right?
Yeah, you gotta do turning points plus 1 will give you degree 5. And on part B, is the leading coefficient positive or negative?
Positive.
It is positive. And what is my minimum degree here?
Four.
Okay, if possible, sketch those graphs. Degree 4 with 4 real zeros and a positive leading coefficient. So I will do a few of these, but there are multiple ways you can sort of do these. As long as it follows what they're saying, I think it'd be okay. If it's a degree 4, how many turning points do I need? So now I'm going the other way. If it's degree 4, I need
3 turns.
3 turning points. It's got 4 real zeros. So another way I can do this is if it's a positive leading coefficient in a degree 4, it's a positive even. So I know I'm going to come in and go out like a positive parabola. If it's degree 4, well, if you go across the axis and come back through, that's going to give you 2. I think we're going to have to do that twice, right? So there's, I think there might just be one way to draw that one. I guess you can move it left or right across your y-axis, but see, it doesn't know how to spell degree. Degree 3. I know I'm skipping B. I feel like you can follow some of these. There you go. So degree 3 with 2 x-intercepts, 2 turning points, and a positive leading coefficient. If it's a degree 3 with a positive leading coefficient, I think the way I usually start this is with the end behavior. It's degree 3 positive leading coefficient. The thing I'm thinking about is a positive line. So my end behavior should look something like a positive line. I know it's degree 3, which gives me 2 turning points, and I need 2 x-intercepts. So if I go across once, this is only going to give me 1 x-intercept. If I go across and come back through, it's going to give me 3 intercepts. So what do I have to do?
Cut to 0, but don't go past it.
Yep, I'm going to hit the 0, around, maybe something like that. And there are a few ways you can draw this. There's a few ways that are correct, a few ways that are wrong. All right, I want to move on a little bit so we can get a little more practice in with some other stuff. So for this function, what is the domain? Find the domain of this thing. So this is a bit of an odd question because I don't think we did this yet with the piecewise, maybe.
It's been a while.
Yeah.
We didn't really talk about domain, although you can tell what it is just by looking at the.
Yeah, we're looking over here.
Yeah.
Where's our x going to go from and to? going to go as low as what, -3. It's going to pick up and it's going to do some piecewise things, but it's going to go up to 4. And so just like going over this right quick, if I want to write this in interval notation, what I'm doing is everything from -3. Interval notation, I'm doing that. And I do include the -3 because this has the equals to. I do include the +4. It has the equals to. We want to evaluate f of 0.
Can I ask a question?
Yeah.
Is this based on the values on either side, or is it based on the order that you were given these piecewise functions?
Oh, what are you talking about? The domain?
So the -3
Mhm.
is the
How
very
far-
first thing mentioned, but it's also the lowest. So I don't know what's making the decision here.
Yeah, they're going from least to greatest here. Well, usually when
Okay,
you do
so regardless of the order.
yeah, usually when you do
Yeah.
piecewise, you're going to go from least to greatest. They're not going to give it to you out of order. You want to evaluate f of 0. So this is one thing I would say. If you give me 3 numbers when I ask you to evaluate a piecewise function, you are absolutely, completely, totally incorrect. Like there should be one thing you give me when I say evaluate f of 0. So with that said, you have to know which one to plug it into. What people will do is they will just start spinning out every single thing, plug in 0 for everything. And it's like, nah, that's not what it means. So my 0 falls in where?
The second piece.
This second piece right here. If I want to plug in 0 minus what I'm doing. If I want to evaluate f of 0, that's going to be
-3.
-3. That's what happens when I plug in 0 to x squared minus 3. If I want to graph this thing, how do I graph this piecewise function?
We have to graph 3 parts and then see if they are continuous.
Yes. So what's the first point on this thing that I'm going to graph? I'm looking where x is a -3. I'm looking where x is a -1. And this first function looks like what? Y equals a -2. Another one looks like y equals x squared minus 3. Another one looks like y equals a -1. And this one is that I'm going to graph. So if you want to do these sorts of things would be a good way to get a grasp on what's happening. And so if I want the point of this, what's the point on this first thing? My xy would be what?
-3, -2.
Yep, -3, -2. This would give me a -1, -2. So that's the first part. That's the first piece that I would want to graph. The next thing I want to graph looks like y equals x squared. X is what? -1. Graph solid dot. I want to figure out what this is. X is a 2. And I want to graph an open dot there. So I'm going to do this. I'm going to do this with each 3 piece, right? And the last one I'm going to do is y equals what? -1. I want to know where x is 2, and I want to know where x is 4. This one is open. This one is solid and solid. Sorry. And so if I get these points, these should be my endpoints. They should give me a pretty good idea of how my graph goes. I know if I plug in a -1 to my x, I get a -1, I square it. I do what? 1 minus 3. I think that should be giving me a -2. Same thing with 2. I do 2 squared, gives me 4. I'm going to subtract 1 or subtract 3. It's going to give me 1. And so we have to plug these numbers back into here to figure it out. Same thing, we're plugging x into this. Oh, look, we don't have to plug it in anywhere. It is a constant function. So these, I hope, should be a little quicker when getting the points from. -1 and 4 minus 1. I just take my x there, I take my y there. And again, like I hope in your brain you think like the first half and the second part of this graph should look like what? They are constant functions. They should look like what sort of lines?
Solid.
Yeah, well, the solid lines that. Oh shoot, graphed it wrong. -3 minus 2. They're continuous throughout themselves, probably. -1 minus 2. Zero slope. So I'm graphing these things. I don't know. I probably can't put this all in there at once. But I'm going -3 minus 2. I'm going to a -1 minus 2. It should be open. And then this one tells me to make -1 minus 2 solid. It tells me to make 2, 1 open. And then I also have a 2, -1 and a 4, -1 that I'm starting with. 2 minus 1 solid. 4 minus 1. So the first part and the last part are flat lines. This part between here and here is a parabola. So this thing is curving. So it looks like x squared minus 3. So the other thing we might want to do is find the vertex of this thing. So it is going from this point to this point, but what is my vertex here? So another way to think of this is like a graph transformation, right? If we'd have an x squared minus 3, what does that -3 do to our x squared graph?
It goes down 3.
It goes
units.
down 3. So instead of 0, 0, I think our vertex would be at what? 0 minus 3? Zero minus 3 should be our vertex. So I think what is happening here is this is my parabola right here. I want to go down to my vertex and back up to this right here. It's not the best drawn parabola, but it should be a parabola sort of shape in there. So being able to draw these things, being able to get your endpoints, and if they give you a quadratic, be sure to put your vertex in there, right? Be sure to figure out where your vertex is and what the curve sort of looks like. Okay, and any questions about this thing? The next thing is what? Is it continuous?
No.
No, it's not continuous. Why is it not continuous? Probably because of this thing right here, right? There's a big gap in there. You got to pick up your pencil to draw it. All right. That was what, 12? 13 says what? Find exact values for all x-intercepts of the polynomial. Did we do anything that was a cubic? Can we do? Yeah, we can do this. We can do this. Finding the x-intercepts is like finding what of your function? What is this asking us to do? How would you find your x-intercepts if they give you
The
this
zeros of the function?
function? It's the zeros of the function. So if we want to solve this, how would you solve this? Really, there's only one sort of way that we have at this point to solve this thing. There are 4 terms. So if we have 4 terms, what's the method to look for?
AC, or not AC. Factor by grouping.
Yeah, so you can put it in your box if you want. But whether you do box or whether you do factor by grouping, we should be able to factor this thing. So if we factor out an x squared from both of these, I think that this is an x plus 3. And what am I factoring out of these 2 things? A little bit weird now that I look at it. I don't think we had anything like this.
We
But
haven't.
we could do it. It's doable.
Absolutely.
We can still factor this thing. And we haven't had really anything like this, but I think we did quadratics. So if I was asking you about quadratics, we could actually set this x squared minus 2 equal to 0 as well. And I think we'll get 2 solutions there. Because we can't really factor this anymore. I think we'll be all right, just setting that equal to 0. 2. This is what? So that's a little bit new, a little bit different maybe, but plus or minus 2. Sorry. Minus 3. But it is building on the concepts that we did do, right? If you want to know your x-intercepts, you set your equation equal to 0, you factor and solve it. Okay. Determine whether the given value of x is a 0 of the polynomial. So how do we see if something is a 0? How would you see if that works? It's like time. Well, I'm going to do one more problem before we leave at least. I know that.
And I put a problem in chat that I thought might be a good one to do.
Yeah,
too.
yeah, I have one exactly like that.
Oh, cool, cool.
I was going to do it before we left.
Brilliant minds think alike, you know?
Yeah. So how do we know if this is a 0? How do we figure that out?
We would convert the y into 0.
And you're doing like y'all are doing too much work for this.
Okay.
If we want to know if this is a 0, what does that mean if I go plug this back in?
It should equal 0.
It should equal 0. So really what you're doing is you're crunching this. And I don't want to do this because it's just a bunch of number crunching. It's not a lot of fun. And you're asking yourself, does that equal to 0, right? You plug it in and you see if it equals to 0 to see if it's a 0. You see if it gives you a 0 in the y. Okay, so that's 14, 15. Use factor theorem to determine whether the given factor is a factor of polynomial. We haven't done that yet. The factor theorem?
No.
Yeah, I wasn't sure about that one.
Yeah, we didn't do factor theorem. 16, the graph of polynomial function, write the polynomial in factored form. Okay, so this one I will do right quick. My first factor is going to look like what? My next factor will look like what?
X plus 2 and x minus 1.
X plus 2, x minus 1. What about the exponential? That's the other thing you got to catch yourself on. So definitely look at multiplicities when we're doing these.
Right.
This isn't happening once, it's going straight through, but this is happening
Twice.
And then they ask about plus or minus 1. It has to have a leading coefficient of
-1.
-1 because it's going down overall. 17. I feel like we just did that yesterday. I feel like maybe doing this other problem before we leave might be the thing to do. 17, the solutions are in the back even, right? 17, 18.
I'm pretty sure they are.
Yeah.
Yeah.
They got the solutions for them, so I don't think that's too big of a deal.
No.
It's like if you can't figure this out from the solution, come talk to me during office hours or something. But I think it's pretty straightforward. We went through it yesterday. You write your factors from the zeros. You write your multiplicities as exponents. 18, what sort of information? I'm just gonna give you like a hint. We should be able to factor all these somehow. So these might be a good way to go through factoring. If you're factoring, what do you want to pull out first? Like this one, we see x to the fourth minus x to the third minus 6x squared. What's the first thing you want to pull out of there? If we're factoring it.
The x to the second.
Yeah, it should be x to the second. If we do that, it gets everything down, right? X squared minus x minus 6. And then we can factor this thing. Was that minus 3 plus 2? We got an x squared. We got x plus 2. And so we should be getting a few different solutions. And there's one other problem I want to go through before we end class. It would be worthwhile going through it. So if I got a problem and I got it here, the sidewalk along the swimming pool, this problem. So we had this problem a few different ways, worded a few different ways. So it has outer dimensions of 20 by 15. The area of the pool is 84 square feet. What is the width of the sidewalk around the pool? We got a sidewalk, we got a pool. It's all the same. Uniform sidewalk is what I should have said probably. And it says the outer dimensions are 20 by 15. The pool is 84 square feet. What they're saying is the pool, that's my 84 square feet inside of there. If I want the outer dimension, along here, 15 and 20. So how do I set up this problem is the main thing that I want to get at. Area is just multiply and length times width to get to my area. But what I want to know is like how long is this thing right in here, right? I want to know how long is this thing right in here. Do you all remember this problem, doing this problem for homework? We had this problem in the notes in homework.
We want to add 2x to both of those, right? To the length and the width.
So if this whole thing is 15, I'll be quiet, Netflix. Oh, come on now. I don't know why I did that. Okay.
Subtract 2x from the length.
You want to subtract 2x. So 15 is going to be the sidewalk. We have the sidewalk. We have the width of the sidewalk twice. We have the same thing happening kind of over here too, right? We have 20. If I do that, this is all going to be equal to
84.
The
The
inside
80.
area.
The area of the pool.
Yeah.
Yep. Now this is a setup. If you do this correctly and you get your setup correctly, I think I'm probably giving you too much, but I think I set things to where they would probably simplify pretty easily. 15 times 20 is going to give me what, 300. I'm doing minus 30x and then 40x plus x squared. Have to do some distribution. If you got to this point, I would be pretty happy. You would get a good portion of your credit for this problem, probably. This is a good, understanding the setup and understanding how to get to here is a good portion of things happening. But still, you still got to carry this on and be able to do some good algebra. So, 300 minus what? X plus x squared. I'm going to rearrange things. I don't want my 4x squared plus 300. I'm going to have to do what? 300 minus 84 to get that over to the other side to make it 0. Plus 216, 0. And like I was saying, if we do this correctly, I think everything now should be divisible by 4, so it should simplify it a little bit. Make it a little bit easier. 70 divided by 4. Oh man, it doesn't. Everything is divisible by what? 2? Everything is definitely divisible by 2. 2 and 6 divided by 4.
Oh no, you should divide that by 2, right? 216?
Did I do that wrong?
Yeah, just make
108.
216 108, yeah.
Did I do this correctly? Let me double check. It's minus 30, minus 40. Yeah, that's it. Minus 70. For some reason I was thinking it would work a little better. Yeah, I guess I'll do it the long way. So 2 times 108 is going to give me back 216. I'm looking at factors of about 216 and 35. That's maybe pretty safe. Or 254, I think. Uh, 216 divided by 8. 27. 8 and 27 do it. 27 do it, huh? Ooh, okay. 8 and 27. So we have 2x squared. And I think I'm going to throw it in the box. Oh, they add to minus 35. They should both be negative. I messed that up. So they should both be negative. I dropped a negative sign on my 35. They should both add to negative. They both have to be negative. Minus 8 minus 27. So I want to do this in a box. I want to throw in 2x squared minus 8x. I want to do minus x. I want to do plus. Between 2 and 27, I don't think I can take out anything. Take out an x. Between 8 and 108, I can take out 4. And I'm going to leave with a negative. Whew. And this, I can take out a 2 and an x. Here, I got to lead with a negative. What is the common factor between 108 and 27? That's a good question. I think it might be 27. It's got to be 27. Huh?
Yep.
Is everything multiplying back through? I guess that's the thing to look at, right? It looks like everything's multiplying back through. I think what you're going to end up getting with is 4. X minus 7 is equal to 0. So we're getting 2 solutions here. One of them looks like 4x is 4. The other thing looks like this thing is 0, or 2x is what, 27. I think if we divide 27 by 2, I know I usually make you do things in fractions.
13 and a half.
I'm going to throw it as 13.5. So we're looking at this thing. I did all this work to solve this stupid thing. What do I get out of it? 4 and 13.5. So which one are you going with?
The 4.
The 4 works when we go plug it back in, so this is definitely a solution. Does 13.5 work if we go plug it back in?
No. It exceeds the length of the sides.
It doesn't exceed the length, but it's not gonna, it's not gonna come up, right?
Right.
It's still gonna be extraneous, right? So this is an extraneous solution. It's not gonna work out if we go try to plug it back in. So if I go to do what? 15 minus 2 times 13.5, I'm gonna end up getting a negative side. Oh, that's what you mean. Yes, yes. Because we get 2 of them, right? Sorry. I wasn't thinking about that.
No worries.
Yeah, if we get 2 13.5s here, right? We're definitely over 15. That's not making a lot of sense with how we have things set up. That's right. It will start giving you negative sides or something weird, right? Any questions? I think we're over. We're a little bit.
No, I think I'm pretty good.
All right. So test tomorrow. Be there, be square. I don't know what to tell you. But I think that's probably the end of the class now, huh?